All right, welcome to this course, NSM KLA course on Introduction to GPU Programming, which is going to be delivered by Pradeep and me. Pradeep is from KLA and I'm from IIT Madras. This is sponsored under the National Supercomputing Mission, and for a few minutes I'll also be admitting students, so I might have to switch the screens. So the idea behind the logistics of this course is that we are going to have 5 days of lectures, and every day the first few minutes are going to be discussed about the previous day's assignment, and therefore on day 6 we'll have a small session on the discussion on the 5th assignment, which is going to be on the DPC++. So we are, as you noticed, we have started the recording, and we'll make the recordings available, and we are not going to really worry about your attendance. The only thing we'll worry about is your assignments, right? So, but we hope that attending the lecture is also going to be helpful to all of you, especially the ones who are starting fresh. And we have already shared information on about everything, all the logistics in a Google Sheet. In case somebody does not have that access to the Google Sheet, please drop us an email and we'll be able to sort this out. The selection of participants for this particular course has been quite stringent, in the sense that you had to be nominated or you had to be a faculty member in one of the institutes to ensure that you can participate. This was not open to all the participants, unlike many other courses that we have conducted under the National Supercomputing Mission. So we anticipate that your learning will be maximum with the assignments, and the certification is of course linked with the assignments. Of course, that doesn't mean that you have to submit assignments if you are doing this course, but we believe that the learning will be better if you actually work on the assignments. Some of you might have some prior experience with CUDA programming, and but we are going to assume nothing of that sort in this, and therefore we'll be starting from the ground up. That also means that you should ask questions. Right, so this course is for you, and therefore you should be asking, even if it's a simplest doubt, feel free to ask. We would prefer to have this as interactive as possible. You can directly unmute yourself or put your question in the chat. Either way is all right with us. And to help us with the assignment evaluation, Ashwin Kumar, who is a PhD student at IIT Madras, and Kush Jogi, who is an MTech student here. They are going to help us with the CUDA and DPC++ respectively. Yeah, one more logistics with respect to the computation is that you need to have access to an NVIDIA GPU for the first 4 assignments, and also to Intel Dev Cloud or some Intel GPU for the 5th assignment. Right, so it could be on your laptop may have an NVIDIA GPU either on Linux or Windows. It's all right. Either way should work out. Almost all the programs should work irrespective of the operating system. I'm not sure about the Mac. Students have told me that they face some issues with running it on Mac, and therefore Linux or Windows is something which you might have to arrange for. Alternatively, your institute might have some cluster which might have a GPU installed, and if you have access to it, that is another option. Alternatively, there is Google Colab or Kaggle, or there could be other websites also which provide access to GPU. Even if it's not a high-end GPU, it is all right. Most of our programs should be easily doable on a reasonable GPU, right? Even if it's a lower-end GPU, it might all right. Yeah, it might be all right. At the same time, I would also say that while we are discussing this in class, that is during the online lecture, if you want to try out those programs, feel free to do that. All the programs links are given in the sheet, in the Google Sheet. So you should be able to just navigate through the programs, which program we are trying out, and feel free to do that during the class and ask questions. We are okay with that. So I would like to hand it over to Pradeep at this stage. Pradeep, you want to add anything?
No, a couple of things I just want to reiterate what Rupesh said. One is the assignments are really the learning. So I would strongly encourage you all to take the time and try to do the assignments. The assignments are not uber complicated. They really enable you to digest the lectures. So I would strongly encourage you. Rupesh, do we have any expectation from the assignments that you want to highlight?
I mean, yeah, we have the public test cases. So as long as those pass, they should be able to get at least a few marks. But we expect that, I mean, it's not, we only check for correctness, but performance is something which is left to the participants.
Wonderful, thanks. And the other thing I'll say is this really is an introduction to GPU programming, right? So for those of you who are following the news, and I'm sure a lot of you are very excited about AI, right? Really, the magic of AI today is enabled because of hardware, and that is GPUs. So even if you may not be looking to work actively on GPU programming or on GPUs or on hardware in future, having a good understanding of this fundamentals of GPU programming will really enable you to progress forward in your undergraduate, postgraduate studies or whatever, right? So it's a fantastic course for introduction to GPU programming. It's 5 days. Please focus. I liked what Rupesh said. Don't look at WhatsApp. Please try to focus on the lecture. Try to do the assignments. And if you like the material, there's lots of subsequent material that we can point you to that's available online to go deeper. But this gives you a wonderful breadth of experience. And the other thing that Rupesh and I have been trying to educate people on is that while a lot of the lectures will focus on CUDA, there is a big push today to not use only CUDA to program the GPU, which is something also this class will cover, which is a little unique compared to a lot of the other GPU programming classes that you will find online. So I encourage you to use this opportunity. You have been nominated, ask a lot of questions, do the assignments, and do provide us with feedback on how we can continuously improve this course. Thanks. Thanks, Rupesh.
Thanks, Pradeep. Okay, so at this stage, before we delve into the technical aspects, anybody has any questions? Okay, so if you have any questions, feel free to interrupt me or put it in the chat. So we'll go ahead from here and we'll start looking at the first part, which is going to be the computational aspects of CUDA. In general, when we talk about GPU programming, right, it must start with some sort of a graph, right, where we show over the years how things have changed, right? Those things could be related to the CPU frequency, or it could be related to power and so on, right? So since this is an abridged course, I'm not going to get into that, but at a high level, the philosophy is about the philosophy of parallel programming is that yeah, so earlier, as we call as good old days of software, is that you have a program and then you run it on your computer, and let's say that finishes in 10 seconds, right? After 5 years, you have a new hardware and you run exactly the same program, and instead of 10 seconds, it completes in, let's say, 8 seconds, right? And you can show it to your manager or your PhD guide is happy that it is working nicely, it's working better, right? Although you have not done any changes to the program, right? So those were good old days of software, and that was happening because of the architectural changes. In particular, the clock frequency was improving. At some stage, early 2000, we realized that that is not going to work any further, and therefore we have to do something about it to improve performance. And the only way to do that was to go parallel, where we have enough transistors. We can pack those up into a chip, but we need to make use of them. So therefore, putting it onto a single core was not a possibility, but putting it across multiple cores was. And that is where, although parallel programming has been there since probably 50 years now, but it provided this particular restriction, provided an impetus to parallel programming as well as parallel programming models, languages, quite a bit that way. And earlier, the ways we used to program was identifying across instructions what instructions are parallel and find it out which can be executed in parallel, etc., using instruction level parallelism. What CUDA showed us is that, or what GPU showed us is that that may not be always the best way to perform to extract parallelism. There is also something called as a data parallelism, which is in general scalable, right? So this course is primarily going to be focusing on first 4 lectures to be focusing on CUDA. And in the last lecture, we are going to explore beyond CUDA computation. So let's start with our hello world, right? So this is a C program, right? And as you can see that there is no construct which is related to CUDA programming or GPUs, right? So I take this simple hello world, there is a printf, I compile it, but instead of using GCC or G++, I'm going to use NVCC as the compiler. And I store the file as .cu extension instead of .c or .cpp. And when I compile it, it compiles. And when I run it, it gives me the expected output. Right? What that indicates is that all your C programs, you will be able to run using this new compiler called NVCC, right? NVIDIA C compiler. And just that we need to probably rename our files to .cu, which is for CUDA. Right? So that turns out to be good. And that means that all your C programs will run. But are these programs running on the GPU? No, these programs will still run on the CPU. Okay. So let's come to the GPU part. So the GPU hello world is going to have slightly different syntax, and let's understand it carefully. Right. So there are typically 2 parts to it. One part is called as a kernel, right, which is a function which is going to be running on the GPU. It will not run on the CPU. It will run specifically on the GPU. And then we already have this main, in which we need to ensure that we call that particular function, which we term as a kernel launch. The kernel, apart from that, we need to also include this CUDA.h. So the kernel is designated with __ global. These are 2 underscores. Global, sorry about that. __ global __. And then there is void, whatever function. It can have parameters also. And currently it's just printing hello world. Right? When we start from main, we call this kernel, and then there is right, and that there are numbers separated by a comma. For now, we'll not worry about this particular syntax, but it's the syntax to call a function on a GPU from the CPU. And that 1, 1 indicates how many threads are there. A multiplication of these 2 numbers is going to tell us should be executing this function. Okay. So in this case, 1 into 1, it's only single thread, and therefore only 1 thread is going to print this hello world. That is the expectation. So we expect that this should also be compilable with NVCC, and when I try to compile it, it does compile correctly. But when I try to run it with a.out, I unfortunately get no output. So that's a little bit of anticlimax. I understand that first GPU programmer, it's not giving any output, but that is what you will mostly encounter. And that happens because we are we have not yet studied that CPU and GPU are 2 separate computing devices. And therefore, what CPU does is that it calls this kernel, calls this function, GPU function, and goes ahead. Right? So after this dkernel is launched, after this, the CPU starts going ahead and it starts executing the next instruction. Right? In that sense, one might view this as an asynchronous kernel launch, and the CPU and the GPU can actually simultaneously execute their code. So if there would have been a printf after dkernel on CPU, it would have executed that while the GPU is trying to process the printf hello. Okay. So it turns out that there is nothing after this, and therefore it just finishes. And whatever was printing getting done by the GPU, that is not brought back to the CPU, and CPU doesn't, let's say, flush the output buffer, and therefore we get no output. To ensure that we see the output that is printed by the GPU, we have to ensure that the CPU waits for the GPU to finish its execution, to ensure that the CPU prints whatever is printed by the GPU, because finally the screen is in the control of the CPU. So the GPU is going to, although there is printf in the GPU part, that is only at the language level, it's going to be written to an output buffer. That output buffer is copied from GPU to CPU, and then the CPU is going to actually push it onto the screen. So this pushing it onto the screen requires that the CPU waits for the GPU to finish its execution, and that is indicated with a function called CUDA device synchronize. So that CUDA device synchronize, when I put, then we start seeing hello world. And this time the hello world is not coming from the CPU, but it is being printed from the GPU. Okay. So this is a simple program which is running on the GPU, and we expect that when you have access to a GPU, you should be able to take this program, compile it with NVCC, and when you run it with a.out, you should be able to get this hello world as the output. If you do not get, that means there is some trouble if you don't get this output. Any basic questions on this part so far?
Sir, Abhishek here. So the whole point of printf in D kernel was to just push the string onto the buffer managed by CPU, is it?
That is correct. In fact, the GPU does not have direct access to the our screen, and only CPU has, and therefore GPU gets used more like a co-processing engine. Right? You might have sometimes heard that GPU is a co-processor. Right? So which means that it's not going to be, for example, you won't be able to probably boot from a GPU. You'll have to boot it from the CPU. Whenever CPU expects some computation to be done, it's going to be offloaded to the GPU. GPU will do some processing and get it back. So in this case also, it just printed something, but that printing, although the function is printed, it gets implemented in such a way that it writes it to an output buffer. That buffer gets copied and printed onto the CPU screen by the CPU.
And the printfs are ordered, right? I mean, the buffering is in order. That's what.
Okay, so the printing from one thread is ordered. What that means is that if we are writing multiple printfs from the single thread, let's say hello world 1, hello world 2, hello world 3, these will be in order. But then if you have multiple threads writing to the buffer, then it's possible that their outputs might get mixed. Right? And that's something which we will study very soon.
Thank you, sir.
Yeah. Thanks, Abhishek, for asking the
Hi.
first questions of the course. Yes,
Hi.
Samir.
Yeah. So this like a CPU, how many cores and how many nodes I have to, what number I should change?
Right. So this particular program works with a single GPU, and by default it is, so the GPUs on your system are usually numbered 0, 1, 2, 3 nicely. And by default, it's going to take the first GPU, that is device 0, and run our code on that. If we want to use a particular GPU, we might have to use a particular command called CUDA set device, to which we can pass a parameter 0, 1, 2 like that, and that is going to use that particular device. So if there are multiple GPUs, then CUDA set device is required. As far as node is concerned, it's going to be the node on which we are running this program. Right? So there is no MPI currently here, and only it's as if we are running a C program locally, and that is how the CUDA program is also going to be run on the current.
Okay. And how many numbers or number of cores, how to decide that?
Right. So the GPU, so the GPU per se and the GPU hardware and the CUDA program, these might not have a one-to-one correspondence. For example, your GPU might have, let's say, a few thousands of cores, whereas the CUDA program that you might launch might have a few, like in this case, one, or it might have large number of threads with which we can launch. For example, I might be able to launch on the GPU with millions of threads, right? But that doesn't mean that all of them will be parallel. It will be always decided by the hardware limitation. So if you have, let's say, 3,000 cores on your GPU, then 3,000 threads will be can be simultaneously active at any point in time.
Yeah, okay, yeah. Thanks.
Yeah, I'll also show you some notes with respect to some of the number of some hardware, let's say, characteristics of typical GPUs. But yeah, if there
Sorry,
are,
sir, I have a simple question.
yes, Sam, go ahead.
Yes, so on this CUDA device synchronize, will it say only for the output buffer transfer, or if we have some matrix or array, then memory also will get copied from GPU to CPU through this?
Okay, that's a question, and you are aware of the class. Will this work only or if I have if I have a matrix or array, will that get automatically copied across the CPU and GPU? By default, no. And what we'll have to satisfy that question, what we have to do is to transfer the data explicitly from CPU to GPU, run the kernel there, which performs the computation on that array or matrix, get the results back, that's copy the data back from GPU to CPU, and then process it on the CPU. Right? And this needs to be done because the CPU and the GPU memories are integrated. Sorry, the discrete GPUs are different. That is physically different, and therefore, by default, we won't be able to access the other memory from the other device.
Okay, thank you.
Sir,
Yeah,
one last
Sandeep has a question
So-
in the yeah. Abhishek, go ahead. Yeah.
So we actually don't need studio.h, stdio.h here, right? Because the printf implementation used by CUDA is something different. Do we still need studio.h here?
Yeah, I'm sorry, I just missed that first part. Could you please repeat that, Abhishek?
Sure. So do we still need stdio.h because the printf implementation used by CUDA is different from the CPU printf, right? So do we still need stdio.h?
Yes, that is true. At the same time, we in this particular case, we might not require stdio.h. If there is a printf on the CPU, then we might still require. But even without that, I think it will probably give a warning and it will still compile, right? Because the std, I mean, the printf implementation is there in libc.so, which is anyway going to get linked. Right? So it's looking just for the signature, which by default it should be able to construct. That's right. So Sandeep says that NVCC hello.c is working for compiling CUDA C code. If we write CUDA C++ code, what changes we need to do to get the work done? We can use NV C++ to compile that. But I think the recent versions of NVCC also support the CUDA C++. So my guess is, although I have not tried, but my guess is that NVCC should still work with the C++. If it doesn't work, then you can always use NVC++. Bhargav Manohar says, even after including CUDA device synchronize, I get no output, but when I tried compiling by giving the GenCode flag, then I started getting an output. What could be the problem? Sorry, I didn't understand this GenCode flag. What was that?
Hello.
Yeah, go ahead.
So I checked online about how to compile, and I've seen one of the make files of the NVIDIA sample codes. So they have these flag called GenCode, and they specify the architecture and the code for each GPU specifically. And
I see.
yes. So for my particular GPU, I searched the code, and then I gave the flags, and that is when it started running. So
Sure.
what is the
Yeah. So yeah. So there is a command line argument to NVCC which can specify that on which architecture or for which architecture I want to generate code. So this NVCC can generate code for multiple architectures of the GPU, and that seems to be what that GenCode is doing. Although I mean, there are multiple ways in which this can be specified. GenCode is one, -arc equal to SM underscore something. might be another. In general, I think it should have worked. I'm a little surprised that it didn't work without that. But nonetheless, if that gen code is working, maybe Bhargav, if you could put your command line which worked for you in the chat, that might help the other participants also.
Sure, sir, I will do that.
Thank you. Any other questions at this stage?
Sir, the dkernel invoking statement, one is there. So what is the meaning of first one? Second one is number of thread. First one is?
Actually, both of them will signify the number of threads. Currently, we are saying that a multiplication of these two is going to give you the total number of threads with which the kernel is going to run. What those two numbers are, we are going to study. The first one is called as number of thread blocks, that is groups of threads, and the second one is the number of threads per thread. And therefore, the total number of threads becomes equal to the multiplication of these two. We'll study that in a while.
Okay, in second kernel, so we are invoking another kernel, assume that. So first kernel, we have 3 thread. Second kernel, also we have, say for an example, 5 thread. So the thread, now if we print the thread ID, so ID will be continuous, so randomly it will be selected.
We'll have to get to thread ID in a while. But yes, you are right. But it won't be random. The thread IDs are always going to be 0, 1, 2 like that. So in this case, the thread which is running this printf is going to have the thread ID as 0. If I launch it with 1, 3 or 3, 1, then the thread IDs will always be 0, 1.
Okay, thanks.
No problem. Yeah, thanks Bhargav for the command line. Yeah, Shikhar, you have a question?
Yes, sir. Sir, about this global specifier. So, sir, by default, in C programming system, all functions are global in the translation. So, is this explicit global keyword needed?
Yeah, I'm very sorry, Shikhar. I'm not able to hear you properly. Could you please be closer to the mic or speak louder?
Yeah, am I audible, sir?
Yeah, better. Yeah, go ahead.
Yeah, sorry for that. So, sir, my question is regarding this global global specifier. So, look, by default in a C program, all the functions are always in a global state in a translation mode. So, is this global explicitly needed?
Okay, if I understood correctly, you are asking that in C, all the functions are anyway having a global scope. So, what does this indicate in a CUDA program?
Yeah, exactly.
Okay, okay. So this global specifier is not present in C. This is a special keyword supplied specifically in CUDA, which indicates that the function which is marked as global is going to be a function which is running on the GPU and callable from the CPU. Global indicates that the function is going to be running on the GPU and callable from the CPU. As we will see soon, there will be another mnemonic called __ device __, which will indicate that the function is running on the GPU and also callable only from the GPU. Right? And similarly, there is __ host __, which essentially indicates the CPU-like function.
Understood.
Sure. Any other questions?
So can we have the regular return types for this global function?
Yeah, so as far as globals are concerned, I mean, the kernels are concerned, those cannot return anything. So it has to be always void. Yeah, that is a restriction by the CUDA programming language. But nonetheless, if you want to return some particular value, then we'll have to put it into memory and copy it back. Because the CPU, GPU memories are different, we need to make it explicit. So therefore, by default, they have decided that it will not return anything. All right. If there are no further questions, then we'll move ahead, and thanks for all these questions. So our first takeaway was that CPU and the GPU functions, these run asynchronously. That means they can be running in parallel, and we have to be aware of that all the time and add this CUDA device synchronize whenever required. Okay. So So I'm going to make life little more complex. So our D kernel is now copied 3 times. And then there is CUDA device synchronous. Okay. So what is going to be the output of this code? Let's understand that. So D kernel 1.1 gets launched, and it's going to print this hello world, and similarly that hello world is going to get printed thrice. But is there something which is different than this possible in this particular program is what we have to see, right? For example, there is printf on CPU. Is it possible that this on CPU might interleave with these 3 hello worlds, right? Anybody wants to give any suggestion on that? The question is it possible that you can get an output like hello world on CPU, hello world, hello world? Sandeep says no. Yeah.
No, sir.
Okay. Maruti says no. And yeah, I'll wait for a few seconds. Shomi says no. Multiple of you are saying no. Chinmay, Hitesh, Shubham, Arhan, Satya Bhagwan. Okay. So you all are right that it cannot give this output because there is, we said that there is CUDA device synchronous and CPU is going to wait until the GPU finishes its processing. In this case, the processing is all 3 kernels. So all the GPU related instructions before this CUDA device synchronize are going to finish. Only then the CPU is going to move ahead. But then now I'm going to ask another question. So this part is correct. Now the second question is it possible that the second D kernel prints its hello world before the first D kernel prints? Right. So Chinmay says yes. Satya Bhagwan says, all of you are saying yes. Okay. So with whatever we have studied so far, it seems possible. Although that will not happen, and I have not told you the reason, but let me get into that now. Right. So let's understand. Yeah. So as Sandeep said, maybe there is a queuing happening. Yes, there is a queuing happening. So let's understand how, why one might think of getting the second hello world getting printed first, right? So because we said that the CPU is going to launch this kernel and move ahead. That means that it is going to again launch the second kernel and move ahead. And therefore, it's possible that these 2 D kernels might be executing in parallel, at least with our knowledge so far. And therefore, it's possible that the second D kernel might print something and the first D kernel might be a little delayed. Right? And the same thing can happen with the third D kernel. Interestingly, what happens is that all these kernels, when the CPU launches them, these are not triggered immediately. These are pushed to a work queue. Okay. And as you can imagine, the name work queue itself indicates a first in, first out order. So the first D kernel is pushed into this queue and CPU moves ahead. GPU at some point in time is going to empty this queue in the order it was pushed. So the first D kernel is pushed, the second D kernel might get pushed, and the third D kernel might get pushed into this queue in the order, in the program order. And therefore, while emptying, these also get pulled out from the queue in the order in which they were inserted. And until the first D kernel is done, the second D kernel will not be pulled from the queue. And therefore, there is always a sequential execution of these 3 kernels across. I mean, individual kernel might be parallel, but only if the first one is finished, then only the second one is taken for execution, right? And therefore, in this case, we will never see an output which says that the second D kernel's output is coming first and the first D kernel's coming second and so on, right? It's always in order with respect to the kernel invocations. Does that mean that you cannot have parallel kernels? Well, you can have, and that queue is something which is going to give us an idea that instead of one queue, if we use multiple queues, then you will be able to get parallel execution, which are called as streams, which we'll study a little later. So as Sandeep was hinting at, he was not sure, but maybe queuing the request. Yes, there is a queuing of the request happens. Somik says the kernel pushes the output to a buffer, hence might be serialized. No, not because of this reason. but it's possible that if these two kernels were parallel, then the second one might push first and then the first one, and therefore the outputs can get mixed up, right? But although that is possible in parallel queues or streams, it is not possible with a single stream. There is a single work queue which we are operating. Okay. Any questions on this so far?
Sir,
Yeah, go ahead.
so even with a single queue, the GPU once it pulls out one work order and assigns it to one thread, it need not wait that work to be completed to pull out the second work, right?
It does. So that is the semantics of this work queue, that until the first, so it is taken for execution, and the GPU is going to wait for that particular kernel to be finished before it takes up the second. So there is no parallelism within a work queue. It's completely sequential.
Thank you, sir.
No problem. All right.
And these kernels within a work queue may share data as well.
These kernels within the work queue can share data. For example, the first D kernel can write something, and the second D kernel, when it gets launched, might read something from that data item. That is possible. Okay. Sandeep says that is it better to say kernel call or kernel invocation here? Okay, let's get to the nomenclature correctly, as Sandeep has rightly pointed out. So there are two parts. One is kernel invocation or kernel call, which is only pushing it into the queue, work queue. I mean, the CPU pushes it into the work queue. And then there is kernel execution, which is actually the execution of the code. For example, this printf hello, right? So that is correct. So there is kernel call and kernel invocation, which well, we usually use kernel invocation as the term, not really kernel call. So and kernel execution. So we'll use this term, kernel invocation and kernel execution. Good. Shubham says, then where is the parallelism happening in GPU? The parallelism is currently not there because we have launched the kernel with 1.1. As we launch it with maybe 1,100 or 1,1000, then we'll have parallelism, right? We'll come to that in 2 slides.
Hi, can you hear me?
Yes, Amir, go ahead.
Yeah, so this is like a serial programming in the CPU. So what will happen? What the advantage of this? Like a architecture, the computation will be much faster compared to the CPU, is it?
No. In fact, the computation of the D kernel might be slower on the GPU because the clock frequency of the GPU is lower than or much lower than that of the CPU. For example, typical CPU clock frequencies might be even 3 gigahertz or more than that, whereas typical GPU clock frequency might be 0.7 gigahertz and so on.
Okay.
So the advantage we will get is not here. The advantage we will get is by parallelizing that 1,100. So far, whatever we have seen, these are all sequential toy examples, and nothing beneficial with respect to performance is going to happen. When we launch it with large number of threads, at that time, we will start getting the benefits out of the GPU. So if we launch it, let's say 1,1000, then you will start seeing some advantage. But of course, not with printf, maybe some array or matrix operations. I'll take the next question. Somik says, is this phenomenon only possible for single streams or mostly for the default stream? It's possible for any single stream, or stream meaning a work queue. It is possible. So what we are currently discussing, that work queue is the default work queue. But what Somik is suggesting is about the named streams, which we'll study later. So is that possible with those streams also? Yes. If there is a single stream in which we are pushing all the kernels, right, then those are also going to be sequential. Only across streams we start getting the benefit of parallelism. All right. So now I'm going to give you some work with. Now you are asking me a lot of questions, so let me ask you one question. Right. So I have modified the program. And I still have 1,1. So it's a completely sequential execution of the GPU kernel. And then I have added some printfs, right? CPU1, CPU2, CPU3, CUDA device synchronize, and then on CPU. I would like to know which of these printfs can execute in parallel. Okay, so there are some printfs which can execute in parallel, either on the GPU or across CPU and GPU. And I would like you individually to think about what is possible in to be executed in parallel. And it's possible that it might happen across executions. I mean, for example, if there are two printfs which can happen in parallel, then on one execution it may happen, on another execution it may not happen, and so on. So that is non-deterministic. We don't know about possibilities. That is what I would like individually everybody to think about, and maybe wait for a few seconds, and after a few seconds you can start putting your answers in the chat so that we can discuss this. So I'll wait for a few seconds. Please think about it. Okay, so any suggestions on what can be executed? Okay, so there is some answer. Printf in the kernel and the printf in main will be in parallel. Okay, all of them or some of them? Chinmay says hello world dkernel and printf CPU1. Okay, these can be in parallel. Okay. Somik says first kernel call with first printf, second kernel with second printf, third kernel with third printf, and last printf not happening in parallel. Okay. Science says hello world and CPU print statement just below it can execute. Yeah, similar to what Somik was saying. Soumya says printf in the kernel code and printf in the CPU code can happen in parallel. Okay. Nitesh says kernel call 1 in parallel with CPU1, CPU2, CPU3. Okay. Samir says printf CPU1, 2, 3 can execute in parallel. Okay. Abhijit Ashok says CPU 1, 2, 3 will be first, then kernel, then final CPU. Okay. And Maruti Sairam says kernel 1 first, and then kernel 2, CPU 2, kernel 3, CPU 3. I see. Okay. Okay. Binong says printf CPU 1, 2, 3 and kernel calls are parallel. Abhishek says CPU 1, CPU 2, CPU 3 in sequence, and that is in parallel with hello world on CPU. Okay. Trirak says CPU 1, 2, 3 and 3 hello worlds. Okay. Pirapuraj says CPU 1, 2, 3, then on CPU and then hello world. I see. Okay. Vikas says K1, K2, K3 on parallel. All right. So as you can see, there are multiple answers coming up, right? And let's see, right? So, okay. So let's discuss this. Let's understand, improve our understanding. So let's think from the CPU perspective first, because we understand that better. So as far as this CPU1, CPU2, and CPU3 are concerned, right? Those have to be executed in sequence because the CPU is going to execute those. So that is all sequential. So these cannot be in parallel with each other. Okay. As far as on CPU is concerned, that is after CUDA device synchronize, and therefore that also cannot happen in parallel with the GPU process, okay, as well as the other CPU processing also. Okay, so this part should be clear so far. Now, when we talk about CPU1, right, is it possible that it can be in parallel with the hello world? We said that dkernel launch happens and then the execution is asynchronous. So the CPU is going to move ahead from here and start executing this printf. And therefore, CPU 1 can happen in parallel with the first D kernel's hello. That part seems to be fine. Okay. But will the CPU launch the second kernel? That is the question. Will the CPU launch the second D kernel without completing printf CPU 1? That is not going to happen because printf CPU 1 is a regular instruction. It's not asynchronous call. That is, I launch printf and move ahead. That doesn't happen. Printf is going to complete execution of printing CPU 1 and then only move to the D kernel, the second D kernel. And therefore, CPU 1 cannot be in parallel with the second hello. It can be parallel with the first hello. I hope this point is clear. If there is any confusion, please ask. In a similar manner, when we go to the second D kernel, it's going to print hello world at some point in time, but because it's an asynchronous launch. But does that mean that the first D kernel is over? Well, that is not guaranteed, but the second D kernel cannot get launched until the first one is over. Right? So the second D kernel cannot print its hello world until the first D kernel has printed. So Vikas says I should repeat, sure. So let me focus on these two parts. Right? So we said that the printf CPU 1 is going to happen at some point in time, and after that there is D kernel, which is going to be asynchronous launch on the GPU. So the question is it possible that CPU 1 happens in parallel with the second D kernel's hello? So that is not going to happen, because until the CPU completely prints CPU 1, it is not going to go and execute the next instruction, which is the second invocation of D kernel. And therefore, CPU 1 is going to be fully printed before even the second D kernel gets into the work queue. But when it gets into the work queue, at that time, as far as the first D kernel is concerned, is it already over? We don't know. It was only pushed into the work queue. It might still be in the work queue. While the CPU printed CPU 1, the first hello world might not have been printed at all. So CPU 1 and first hello world can happen in parallel. Okay, but CPU 1 and second hello world cannot happen in parallel. What about CPU 2? In a similar manner, the second D kernel gets pushed. The second D kernel gets pushed. And then the CPU moves ahead and starts printing CPU 2. Right? And this CPU 2 can execute in parallel with what? With whatever is there in the GPU work queue so far. And what is there in the GPU work queue? The first hello world and the second hello world. That is the first D kernel and the second D kernel. That means that printf CPU 2 can execute potentially in parallel with first hello world or second hello world. But it will not will it happen? Yeah, but it will not overlap with the third hello world, because the third hello world is going to be printed using this third D kernel, which is not going to get invoked without CPU 2 is over. That is, printing by the CPU is over. Okay. So what does CPU do? It launches D kernel 1. Then it executes completely CPU 1, and only after that it goes to second D kernel launch, and it just pushes it to the work queue. It moves ahead and starts printing CPU 2. At this stage, CPU 1 is already done, right? But the first hello world or the second hello world may not have been printed. All right. CPU 2 happens, and therefore the two CPU 1 and CPU 2 are guaranteed to be printed. Only after that the third D kernel launch invocation happens into the work queue. At this stage, is the first D-kernel done? We don't know. It might have been done, may not have been done. And therefore, CPU, when its CPU moves ahead and prints CPU 3, it might potentially overlap with the hello world of the first or the second or the third invocation. Okay, so that is to say, CPU 1 can overlap with the first hello world, CPU 2 can overlap with first or second hello world, and CPU 3 can overlap with first, second, or third hello world. So I hope this answer is clear, and if there are any questions, please feel free to ask.
Sir, but we are calling that CUDA device synchronize after all three printf, CPU 1, CPU 2, CPU 3. So completely it will print all these CPU 1, CPU 2, CPU 3, and then it will invoke this CUDA device synchronize. Is it correct?
That is correct. See, our printf on the CPU is the regular printf. So when we say that there is a printf 1, printf 2, printf 3 in a C program, these are always going to get executed as 1 completely, then 2 completely, then 3 completely. Exactly in a similar manner is going to happen with respect to these 3 printfs, irrespective of whether CUDA device synchronize is there or not. So even if you don't have CUDA device synchronize, still 1, 2, 3 are going to be sequential. Only because of CUDA device synchronize, that synchronization or coordination with the GPU happens, and it ensures that the 3 hello worlds are printed. Only then the CUDA device only then the on CPU is going to get printed. Right? So the CUDA device synchronize is with respect to the GPU hello worlds and on CPU. It's not for CPU 1, 2.
Suppose I put a CUDA device synchronize at each of the printf after, means CPU1, then CUDA, then it will be sequential, is it?
That is correct. So if I put CUDA device synchronize after each D kernel, then it is guaranteed that the CPU is going to wait for that D kernel to be over and then only start printing CPU 1 or CPU 2 and so on, which means that it is going to be completely sequential. First GPU prints, then CPU 1. Then GPU prints second hello world, then CPU prints CPU 2. Then GPU prints hello world 3 and CPU prints CPU 3. Then CUDA device, then on CPU. So this Samit's question also indicates that if you want to avoid this problem of what happens on the CPU and GPU, it is best from the perspective of sequential thinking that you put CUDA device synchronize after every kernel call, right? Just to ensure that things are same, and whatever you are seeing on in your editor in the program is actually what is happening. Vikas says GPU function is called by a CPU. It means GPU function is also a line of CPU code. Then why CPU is not waiting to execute the GPU function to execute for the next line? So it's not really a CPU. It is invoked by the CPU, but it gets done as a multi-threaded program on the CPU. So the CPU is going to create a thread, and that is going to take care of pushing it into the queue. And once that happens, then the CPU moves ahead as the parent thread. And therefore, there is multi-threaded processing automatically happening on the CPU. It's not that it's a regular function, right? I mean, it is a regular function call that way, pushing it into the queue, but that gets done by a child thread, and the parent waits for that invocation to happen. Once the child thread has pushed it into the work queue, then the parent thread moves ahead, right? So similar to our fork join kind of parallelism. Any other questions?
So how many such threads can be created?
On the GPU?
For GPU.
Right. So on GPU, you will be able to even create millions of threads.
No. Child thread on the CPU, how many one? I mean, let's say it's a 4-core CPU. So how many threads it can create?
Oh, I see. No. I see. So on the CPU, you can have number of threads. Actually, you can give a large number. For example, if you add OpenMP pragmas there, not directly in the CUDA function, or you are using pthreads or OpenMP, then you will be able to increase the number of threads to a large number. But that doesn't, the number of threads actually gets created is going to be decided by the library. And typically it can be a few times the number of hardware threads available. Let's say on our laptop there are 8 core, it's an 8 core GPU, 8 core CPU, sorry, and then let's say 16 hardware threads are possible with hyperthreading enabled. So you might be able to create 16 or 32 or maybe 48 thread at max, and that is going to be then work sharing your processing, right? So on the CPU you'll be able to create only a few threads, a few tens of threads. But since the GPUs have more number of cores, a few thousands of cores, we'll be able to launch it with a much larger number.
Another question, this CUDA device synchronizes, it reads the buffer, right? So suppose we have a big program in the first kernel launch, then buffer can be flooded. I mean, how to control that?
Are you asking if there is a large amount of printf, then the buffer can be? Yeah, so that is possible. So is it possible? So the question, okay, let me rephrase the question for the audience. Is it possible that large number of threads are there in the D kernel? Let's say 1000, 1000, I launch it like that, right? So there are 1 million threads with which the kernel is launched, and everybody is printing a large amount of output. And this buffer is going to be having some limited capacity, howsoever large it might be, but it will have some limited capacity which you can exceed. In such cases, is it possible that it will still print the correct output? No. It's possible that your buffer might be full and you might not be able to get the exact output. Let me just quickly add my charger. Right. So it's possible that that buffer might be overwritten and it might not give you the expected output as we were expecting, because the buffer might get full and therefore it might not give the correct output. I mean, it will give some last output which is currently inside the buffer. The hope with that is, I mean, the expectation is that typically on the GPU, the computation should be done with number crunch. It should not be used for printing, right? So therefore, we usually, I mean, this printing mechanism is given more for debugging and basic understanding purpose. So we should not be using too much of printf from the GPU, right? It also affects the execution time considerably.
Thank you, sir.
No problem. All right. If there are no further questions, then I'm going to move ahead from here. I hope there is some interesting discussion happening with respect to asynchronous processing, right? So I'm going to leave you with some exercise with respect to NVCC, where that gets installed, what is mean by a CUDA version, and what is the version on your GPU, and what is this device query, and where it is, right? So Sandeep is saying, is hyperthreading different from multi-threading? Yes, a little bit different. Multi-threading is more at the software side, whereas hyperthreading is something which gets enabled by the hardware. Typically on the Intel CPUs, you might have some instructions being executed by certain threads, and it is using some, let's say, ALU or some functional units, whereas some other functional units might be still not getting used by that instruction. So you might start executing part of the other instruction to ensure that the hardware utilization is higher. So many times you will see that the number of cores is X and the number of hardware threads supported is 2X if you go to the Intel website of that particular, or even otherwise. So that typically means that it's a hyperthreading enabled. Right? Sometimes it might get disabled, so you might not see it. But yeah, if you do cat proc CPU info, you'll be able to see how many hyperthreads you will be able to support on that particular machine. Multi-threading is a general concept, more at the software end, where you can have a few cores, but you can have large number of threads running, which can be detached or might not be directly related with the number of hardware threads. Okay. Any other questions? Right. So, yeah. So let's. Okay. So I'll take this question first. Shikhar is asking, Is knowledge about GPU architecture required for this course? If so, can some resources be provided? Whatever is required to understand our lectures, I'll provide that in this course, right? So we will require some knowledge of GPU architecture. We can't do without it. Yeah, so but whatever is required, we'll introduce that at appropriate regular intervals. But there are NPTEL courses, for example, for GPU architecture and programming. Soumya takes it from IIT Kharagpur. So you might want to check out that. There are also other courses, let's say on Coursera, or even otherwise, there are some architecture related resources available. So those could be checked, but you don't really require that for understanding whatever we are discussing in the class. Okay, so let's now make our world a little more parallel and interesting. So now I'm going to change that 11 to 132 and see what happens, right? So when I compile this, it compiles, thankfully. And when I run it, it actually prints hello world 32 times. And that does indicate that there is some parallelism going on. Let's understand where that is coming from, right? So we are saying that 32 threads can execute this particular printf. Note that there is no for loop, right? So when we launch a kernel, we specify the number of threads, and each thread executes the body of the kernel. Each thread executes the body of the kernel. Therefore, there is no for loop. That for loop is kind of indicated in the launch configuration. Okay. So yeah. So before we jump, since Shikhar was asking this question, and I usually get a lot of students from various branches, and therefore we have different backgrounds. So I thought that I'll get some concepts cleared as we go along. Right? So we talk about processes. So all over A.out, Notepad, Chrome, any game you are playing, all of these are different processes which are typically defined as a program in execution. Right? So all these A.out, etc., these are files on the disk. Right? So when you run it, the code in that gets loaded into memory of the CPU, also called as a random access memory or RAM, and then instructions in that start getting executed. Right? So as you start executing this code, that is called as a process, which means the program is in execution, it's running. So even the browser with which you are connecting, that is a process. But it's possible that a process might have multiple threads. Now these threads essentially mean that they are like lightweight processes. They are also execution units, just that there are lightweight, meaning that they might have some sharing across them. For example, multiple threads might share the common data in the global memory. Right? So let's say if you do some malloc, that malloc will be shared by all the threads, and that is very helpful, right? Because if multiple threads are working on the same data, it becomes easier for them to share the data. So let's say that one thread is looking at, let's say I was admitting some students, right? So one thread was looking at who all are trying to enter the Google Meet, whereas one thread was processing the current display of showcasing what is happening, right? Another thread was probably updating, okay, this particular person has joined.
Just one question. So I'm bit thread and code. Is it? Can you explain the thread and code?
Thread and code, you're saying?
Yeah, number of cores and number of threads. So it's a. Can you explain this term, thread and code?
Sure. Okay, so a core is a hardware entity, right? So when we buy a machine, it usually has certain number of cores, which is the actual hardware unit on which the threads are going to run. Right? So that core is like we have memory, like we have disk, like we have fan or power supply. All of these are different hardware entities which come when we buy a machine. Right? And then we need to, as they say, that hardware is the body and software is the soul. The hardware alone is insufficient. We have to put some software or Atma into it. Right? So that software part is the thread, what we call as. Usually, there is also a hardware thread concept I mentioned, which is something which supports how many contexts are supported, how many essentially different kinds of instructions you can execute simultaneously. Right? But at the software level, you might have a different view altogether, where many times we don't even care about how many hardware cores are available. So that we don't, so when we are talking about the software, we talk in terms of a thread. And the definition of a thread is that it's a sequential execution of instructions. Right? So a thread is sequential execution of instruction, and multiple threads can be there and they might interleave. And multiple threads can form a process, which can be a larger heavy duty process which we launch. Okay, so there is a something cores at the hardware level. There are also hardware threads, right, which are the number of contexts that a hardware supports. Then there are software threads, which is typically an abstraction layer, which indicates how they are mapped finally to the hardware threads, right, which are executed by different hardware cores. And since they share some common memory, they are usually called as a lightweight process. So the bookkeeping that is required to process threads by the operating system is relatively small compared to what is required for a process. The concept of operating system comes into picture here, right? So all these are Windows, Android, iOS, Mac OS, all of these are different operating systems. Right? It's a piece of software. It's not a hardware. It's used to manage the hardware. All right. So it's kind of an interface between a user and the machine, because I cannot, I mean, the machine understands binary. I don't speak binary. So I need some sort of let's say, interface to ensure that my commands, let's say a mouse click, gets translated into an appropriate command which is understood by the hardware, right? So this translation of command and management of the various devices, various hardware is done by the operating system. Right? So all our file system, all of these interfaces that we have to work with, the display, keyboard, mouse, etc. All of these are hardware pieces, and we are managing them with our operating system. Bhargav says, is the memory shared between threads? Yes. For the same process, if there are multiple threads, then the global memory is shared. They still have some local memory called a stack, which is going to be local to individual threads. Right. So, like we mentioned, hardware are these whatever things that when you buy a machine or open a machine, you are able to touch and see. All of these forms a hardware part. For example, cache, memory. You will see slots where you can remove and insert more memory, etc. And the cores, which are the actual execution units. So the core is where the finally threads are going to run, right? And you can ignore that last statement. It's unnecessarily confusing, but just briefly to mention that a thread might not completely execute on one core. It's possible that part of the thread might execute on one core, and then the remaining part might execute on another core, and so on. Right? So therefore, I'm calling it as a software thread may jump from one core to another. Right? So that depends upon how the scheduling happens of the threads. Right? What we mean by scheduling is there are multiple threads. Right? Maybe there are more threads than the number of cores. So which thread maps to which core at any point in time? That is called as scheduling. And there are different constraints that we have, that the scheduling should ensure that the work finishes as soon as possible, for example. Right? And there could be other criteria that we might have. Okay. Any concerns further? Any questions on these basic concepts?
Hello.
Go ahead.
So if the memory, the global memory, if it is shared between threads, and for example, if we have some value being manipulated across threads, and if they are existing in parallel, then it is a problem, right?
Okay, so yes, that will be a problem. What Bhargav Manor said is that if there is a common memory, right, and multiple threads are working on it, it's a writing to it, then won't there be a problem? Yes, there will be a problem, and we have to resolve that conflict, right, which we will study in our third lecture, synchronization. Yes, but that is true. So think about it this way, that I am doing, there is some common memory which is initialized to 0. And different threads are incrementing this number. Is it possible? So let's say that there are 1,000 such threads, right, which are incrementing. We expect that at the end of their execution, we get the value of this common memory as 1,000. Unfortunately, that doesn't happen. Right? And we have to put in extra efforts to ensure that that is actually 1,000. Right? So this happens because of this conflict, and we'll study that as we go along. Sandeep says, can you say some major reasons why OS routines are not currently running on GPU? Well, there are multiple reasons. One, there needs to be a market. So currently it has been used more as a co-processor, but there are works happening, at least some research work is happening to ensure that some more aspects of the operating system like virtualization are being pushed onto the GPU. May not be a full-fledged operating system. Because some of the tasks, I mean, not all the tasks should be run on the GPU. Right? Let the usual tasks for which CPU is specialized, let those happen on the CPU, and then whatever are the more parallel data parallel tasks, let those happen on the GPU. So that is the reason why we do not see a lot of these routines being done. But there are, I mean, there are efforts, just that it is not yet mainstream.
So, in the previous example where you were printing hello 32 times across threads, the hello word string is buffered in thread local, or it's global? It's in some kind of global context.
Good, right. So that's a good question, right? So this hello world, is it possible that it might get jumbled up, right? So h of first thread is being interleaved with h of the second thread, like all h together, then all e, and maybe some o and so some l and so on. Is it possible to happen? Thankfully, that doesn't happen. But it's a so they are going to write to a local memory first. These local memories are then going to get pushed into the output buffer, which is going to get then transferred to the CPU. So therefore, jumbling doesn't usually happen with respect to a single printf. Right? So I'm talking about single printf. If there are multiple printfs in the kernel, right? So if there are multiple printfs in the kernel, then it's possible that one printf of one thread, I mean, between the two printfs of one thread, some other thread's printf might come. That is possible. Right? But one particular printf executed by one thread is guaranteed to be without any jumbling from the interleaving from the other.
Sir, can you explain why this jumbling is not happening?
So the jumbling doesn't happen because of the way it gets implemented, that one thread is going to write to some local buffer, and all the threads are going to write to their local buffers, and then these results are kind of concatenated, but concatenated in parallel. Right? And therefore the jumbling doesn't happen.
Hi, regarding this CPU and threads. So just for example, in my system, I did just LS CPU, and the number of CPU is 20, threads per core 1 and cores per socket. So I'm a bit confused with this threads per core and then CPUs. Can you explain these terms?
Sure, sure. So this threads per core is essentially the hardware threads per core. Right, so hyperthreading is likely to be disabled if we see this value to be 1, and likely to be enabled if we see this value to be 2. As the number of cores increase on a system, we need a way to manage them. It's possible that not all the cores you might be able to put on the same die, like the hardware die, and therefore we have a notion of a socket which is going to house a certain number of cores. And therefore, when we say that there are 2 sockets, and let's say 16 cores or 20 cores, then 10 each might be there on 2 sockets. This, I mean, all of these will still have access to the same memory and so on, or the same last level cache. But since these are now 2 different hardware parts, like these sockets, think of those as 2 bags which have some interconnection. If you are accessing some data which is local to a socket, that is on a core within a socket, then that access is going to be faster. Whereas if you are accessing something from a different socket, that access is going to be slower. So those programming performance aspects come into picture. But from the programming perspective, there is no difference. I mean, all of these cores are that way considered to be uniform. So that is, sockets is just an organization of these cores.
Okay, so means, for example, these 20 CPUs are separated in 12 cores per socket. Okay,
That is correct.
And the threads per core, that means each CPU, if it is multi-threaded, then I can say it's a 40 cores or something I can use, is it? Or 40 threads.
Yeah, so if it is 12 cores per socket and it's a 2 socket, then you will have 24 cores available. If hyperthreading is enabled, then that is going to lead to 48 threads, hardware threads available.
And each of the thread can be used for the computations.
That is correct.
Okay, thank you. Yeah.
Sandeep says the code which we are writing is stored in read-only memory where only IP is needed to point to current instruction. Is this specific part is shared between CPU and GPU, or this code is copied to some other location again for GPU? This typically gets copied to the GPU because there is no as such shared memory between CPU and GPU. So although this is read-only, you are right, read and execute, this needs to be copied to the GPU. And that's also one of the reasons when you try profiling these programs, the first kernel invocation might turn out to be a little slower compared to the rest of the invocations. All right, in the interest of time, I might have to move ahead, but please feel free to put your questions in the chat. If I do not have enough time within the lecture, I can answer those at the end of the call. Okay, so let's try to do go further. And what we are going to do is to write a CUDA code corresponding to this C program. Right? So our C program says there is hash defined n as 100, and I'm going to just print the squares 0 to 99. Right? So I would like to print this. I would like you to think of how will you write this program. And if there are any complications that arise when you want to print these values in parallel.
So instead of this for loop, we can get the thread ID and thread ID into thread ID. Then we can print it.
Good. So as Pirupuraj said, this for loop is going to get translated into a kernel, right? In our CUDA context. So this for loop will go away, and each kernel will print something. Now this print something needs to be dependent on the value of I, which requires us to understand to get this value of I separately for each thread, which we can do using something called as a thread ID, right? Which we will use in this mechanism. The other way to do it is to keep it sequential, which I am showing just for the sake of completeness, that you can launch it with a single thread and then have a for loop within that, right? So that is also one way in which it can be ensured. But the question is, can we make it parallel, which is going to be more interesting. So let's do that, right? So there is a special keyword called thread ID x.x, which indicates the thread ID of each thread that is executing. These thread IDs are always going to be from 0 to this particular value n minus 1, right? And therefore, you are always going to get the value 0 to 99. And those, so the output of this is going to be, the values are going to be exactly the squares of 0 to 99. Right? Any questions on this? So as
But this should not be sequential, correct? Because all these.
Right. Very good. So thanks, Abir, for that observation. Right. So the important observation is that these two codes are not equivalent. The left-hand side code, which is the sequential code running on the CPU, always prints it as 0, 1, 4, 9, 16, 25, 36, like that. Whereas the right one may not print it in that particular order because the threads are executing in parallel. Okay? If you want the output to be in exactly the same order, you might want to actually try this particular code, and that will work. Right, and you will get it in exactly the same order. When you want parallelism, you have to get rid of this sequential restriction, and if that is allowed, then you will be able to see these square values, but those may not be in the exact order. Okay? So that's a good observation, and that is what we will have to always think about when we are dealing with parallelism, similar to that hello world and CPU 1, 2, 3, like the parallelism that we were discussing. Any questions on this so far? Okay, so
Just a question in the
yeah,
previous slide. So you said there is no guarantee that it will be printed in sequence when I'm running it in parallel. Is that because the buffer 0 may not have the output for the thread 0, or but when we are reading it, it will be in a chunk, right? Because after this thread invocation and execution, actually synchronization is happening, right?
that is correct. So the synchronization is going to happen after all the threads have printed it, but
Right.
the threads might not print it in the same order.
Because we are running it in parallel.
That is correct. Yes.
Okay. Thank you.
No problem. So the same concept applies even on the CPU parallel programming, right? So if you are using pthreads or OpenMP, then different threads might execute their iterations in different orders, and you might get the output in jumbled up manner. Right? Exactly the same concept here applies. There is little more to it, which we'll come to in a while, but nonetheless, this is fine.
Thank you. Thank you very much.
Okay. All right, so now let's make it a little more complex. And instead of printing it, the squares, I want to store it in an array. That array I am defining, right, of size n, and I would like this code to be parallelized on the GPU. I would like you to think about how this code will look like, and then we'll discuss. Okay, so one thing that we would like to emphasize here, yeah, so Somik has given A of TID equal to TID into TID, that is correct. So that statement should be there. A of thread IDX dot x equal to thread IDX dot x into thread IDX dot x, that is correct. And one might think about passing a parameter now in this case as an array, and that is where we'll face some trouble, right? So A must be global to do so. Yeah, so as Maruti Sairam says, yeah, A might have to be made global. That is one possibility. Let's see. Chinmay says that maybe memory transfer is required, right? So why is memory transfer required, Chinmay?
Yeah, so GPU has different memory as compared to CPU. So maybe we would require to transfer this memory to GPU so that it works upon that and then get it back.
Sure. So let's understand this, right? So we said that CPUs and GPUs might have different memories. Usually they have different memories for discrete GPUs, which means that if I declare an array on the CPU, which is the case in this left-hand side program, and will be the case if we define an array inside main, because main is executed on the CPU. So if the array is declared on the CPU, even if we pass that as a pointer to the kernel, that is not a valid memory location on the GPU. And therefore, we have to explicitly transfer this data across the two devices. Devices meaning CPU and GPU. So therefore, that CPU GPU data transfer is required, and that is what we are going to study now. So let's understand that.
So that means the memory allocation in the main function will not be used by the GPUs.
Yes, that is correct. So memory allocation in the main function on the CPU will not be accessible to the GPU. We'll have to explicitly do that memory allocation from the CPU, but for the GPU, which is what CUDA malloc is going to do, which we are going to study on this slide. So this kernel remains the same as Shomik was telling, right? So we pass an array as a parameter, and we populate the array using the thread ID in parallel. So that part is nicely parallel. That there is no problem. Yes, go ahead.
Sir, excuse me. That if we want to memory transfer, so we need to have we are allocating memory for a variable here in CPU. So exactly same type of variable should be there in the GPU, right? Then only we can
That's
do that.
correct. So can we declare, for example, an int array of n here, right, after the opening brace? Yes, that is possible, but that will be a local variable to that, because each thread is executing the body of this function. So if I create an array there or create variables, those are all going to be local to those threads. We want this array to be global, completely accessible to all the threads. So therefore, we need to declare it in the global memory of the GPU, which is what, and we need to pass it as a parameter. So let's look at the complete program, and we'll discuss more on this if there is any question. Right? So we have this as before on the CPU, and I would like to print it finally from the CPU also, but I want this initialization of squares to be done on the GPU in parallel. Right? So that I'm going to do by calling the kernel with DA as the parameter, where DA I am declaring as a pointer, not an array. And why as a pointer? Because I want to CUDA malloc it, in the sense that I want to malloc it with memory on the GPU. Okay, how do I do that? Just do a CUDA malloc, pass address of that pointer, and then tell how many bytes you want to allocate. Very similar to our malloc with slightly different syntax. And that is going to ensure that DA, which is a pointer on the CPU, DA is a pointer on the CPU, and it points to a memory on the GPU. This pointer is being passed as a parameter to the function call, to the kernel. So that is going to get copied into this formal argument A, and now A is going to point to exactly the same memory which DA was pointing to, right, as a function call parameter, and therefore A points to a GPU memory. So when this code gets executed by different threads on the GPU, that is a fun function, then all the threads which are executing on the GPU have direct access to this memory A, which is allocated from the CPU using CUDA malloc. I hope this point is clear. Once this memory is allocated, we can pass it to the function like this kernel, as we have done at this stage. But then this is populating the memory in the GPU, right, which DA is pointing to. I would like to be this memory, these squares to be printed finally from the CPU. So therefore, since these memories are different, I mean, by the time you are populating this DA here using this A, our A inside main is untouched. There is nothing written so far to our CPU memory. Everything is getting written in the GPU memory. So therefore, we would like to transfer this GPU memory, all the squares, back to the CPU. And that gets done using a CUDA memcopy call, similar to the memcopy function that we have in C. What does it, what all parameters it takes? It takes the destination address, source address. I want to copy from DA to A, GPU to CPU, number of bytes to be copied, and the direction of copy. That is from device to host. In this case, device means GPU, host means CPU. And that also means that you have host to device, which will require anyway when you want to transfer some data from CPU to GPU. So this particular code ensures, let's go step by step, allocation of A on the CPU, creation of a pointer on the CPU, allocating memory on the GPU, invoking a function to write square values to that GPU memory, copying those squares from GPU to CPU memory, and then printing it onto the CPU. Right? That is how we are doing this processing. Let me take up these questions now. Shubham says, does the CPU and GPU have shared address space? Well, no at the hardware level, but there is something called as a unified memory or pinned memory, which is supported for programming purposes, which is uh, uh, perceived to be shared between CPU and GPU, but it's a small amount of memory. Is this physical memory pointer? It is still virtual, but the mapping is going to go to a different device. For example, if you don't do a CUDA malloc and start accessing DA on the GPU, you will get a seg fault on the GPU because that memory is not allocated. Satya Bhagwan says, is CUDA device synchronized not necessary while doing CUDA mem copy, as it might happen that the complete execution was not done. Very good observation, Satya Bhagwan. Right, so we have not added CUDA device synchronize here, right? And isn't it possible that all the squares might not have been written, but the CPU moves ahead and executes CUDA mem copy, right? So that's a good observation. Thankfully, that doesn't happen in this case because even CUDA mem copy gets queued up into the same work queue. So CUDA mem copy will not be executed until the kernel call is over. But to avoid these things, these concerns, like they say, if you don't know what is the operator precedence, you better put parentheses. So in a similar manner, if you don't remember, just put CUDA device synchronize after every kernel call. Good. Any other questions?
Sir, you can't assign to thread ID actually.
Sorry. Yeah, Samir, go ahead.
Okay, so that means we are allocating double memory for each of A array.
That is correct. A is on the CPU, n bytes, n into 4 bytes, and GPU also n into 4 bytes. That is correct.
Yeah, so that means we are limited because the CUDA memory, the GPU memory are quite less. So that means we can't do the high memory computation in the GPU, is it?
That is correct. So if it goes beyond the memory of the GPU, either our program will fault, or we might have to take chunks of data to the GPU, process it, get those back to the CPU, and so on.
Okay, so that means we can't use the CPU memory for the GPU computations.
No, not directly.
Okay. So just for the, so that means what was happening in the printf option, there was no such memory device mem copy we are using, correct? So how it works?
That is correct. So printf internally takes care of that. So when we do printf, that is going to write to that output buffer, which is going to get CUDA mem copy underneath when we do the when we try to print the value from the GPU.
Okay,
That is handled internally by the
printf
GPU
option.
process.
Okay.
But specifically for yeah,
Sir,
Abhishek, you had a question. Yeah, sorry, Pirapura, you had a question. Yeah.
Okay, that in the CUDA malloc, that is allocating memory in the GPU, right? So ampersand DA is giving the memory address from this CPU. So why do we send that memory address?
Why we send that memory address to the GPU kernel, you are saying?
Yes, that's right.
Right. So here, so that memory is going to get allocated using CUDA malloc on the GPU, and then there is a starting address. That starting address is only stored inside this DA. Now that starting address is going to get copied from DA to A, from actual to formal parameter, and since that A is actually on the GPU, it is accessible on the call. So this DA is a CPU variable, but it holds the memory of the GPU memory that is allocated. So just for passing, we are using that as a pointer, because we have to somehow send that memory address. You might do large number of different allocs, CUDA mallocs, but which one to send? For that, we need a pointer to each of them.
Okay.
Abhishek, you had any question?
Sir, is it always the case that thread ID x.x is only read? You can't write to it?
That is correct. It's a read-only variable.
Okay, thank you. And also the CUDA mem copy, you are passing DA to just copy the pointer to A, and then the copy is finally happening on the CPU, right?
This copying is happening via the interconnect between the CPU and the GPU. So the copying is happening from DA to A.
Okay.
That is from GPU memory to CPU memory. And CPU will be involved, and CPU is going to wait till this CUDA mem copy is over. There is a function which allows you to do asynchronously, but yeah, this CUDA mem copy is going to ensure that the CPU is going to finish this execution, only then it is going to go to the for loop. Okay, let me take the question from the chat. Is there any possibility that memory we allocate is larger than the available memory, and what will happen in this case? Currently, I think that is not supported, is what I understand. That is this over provisioning of memory. In some virtualized places, it might be supported at the software level, but not at the CUDA level. So that is not possible. Maruti Sairam says, do we need to deallocate GPU memory after the CUDA mem copy? That is correct. So there is a CUDA free function similar to malloc and free. We have CUDA malloc and CUDA free. So we will have to deallocate the memory using CUDA free function. So CUDA free DA is going to ensure that that memory is free. That is correct. Have a good programming practice. Please follow that. Yeah, otherwise, at the end of the a dot out, end of your program, all the memory is going to get deallocated. Why is that CUDA malloc doesn't return address of allocated memory? Instead, we pass the variable in which we need to store. That is, yeah, this is more like convention in many of these CUDA related function calls, that they all return just an error value, because the CPU needs to understand if that particular function succeeded or not, right? So therefore, this return value is usually the error code, and therefore all the other parameters are, even the reading as well as writing parameters, are passed as parameters.
Sir, one question.
Yes, okay.
Suppose the size of int on CPU and size of int on GPU are different. How does this CUDA mem copy ensure the semantics of what?
That's a good question, right? So is it possible that the CPU int size and GPU int size are different, and in which case will there be an issue? Yes, there will be an issue, but I feel, I mean, I have not tried it, but I feel that even the CUDA installation itself is going to check that this compatibility is maintained between the two integer types, right? The basic word type. So if that incompatibility is lost, I mean, let's say you do some juggling and ensure that it still gets installed and you are able to execute this code, then yes, it's, let's say, integer size on CPU is 4 bytes, whereas that on the GPU is 8 bytes, then it's going to populate only half of the array, or the other way around, in which case there might be seg faults and other issues. Yes, those can come. Right? For example, if you do typecasting and mark it as char star A, right, instead of int star A in the function, then it's possible that you might be accessing some different set of bytes than what is expected. Okay. All right. So at this stage,
Sir, I have a small confusion.
yeah,
So DA, yeah, DA is the location, the address on the CPU memory, or it's the GPU memory?
it's a variable on the CPU, so its address is on the CPU. Just that its value is an address which is coming from the GPU.
Okay.
Yeah.
So
So
if
yeah.
it is from GPU, then at the CPU CUDA mem copy, I'm mentioning first source and then destination, right?
No, destination and source.
Either way, I mean destination and then source. That means these two are different.
These two are typically different. Yes, these two are typically different.
So in the previous statement, DA is the address at the GPU, which is being passed to the formal argument. Then these two are not same?
No. Okay, let's understand this, right? So there is a CPU, there is a GPU, right? They are connected by some bus. Then there is some memory here, and then some memory here, right? So A is allocated on the CPU. DA is also here. So DA, please pardon my handwriting, DA is also here. But there is some memory which is going to be allocated from here using the CUDA malloc. DA is going to point to this memory, which means that DA's value is going to be address of the GPU memory, whereas DA's address is on the CPU memory. right? For example, when we talk about, let's say, int I,
Mm-hmm.
int i's value could be 5 or 6, but int i's address is something different. In a similar manner, DA's address is on the CPU, but its value is some value which is actually an address from the GPU.
Okay.
Right?
Thank you, sir. Thank you. Got it.
Thank you. Okay, there is a question. Does DA point to the dynamic memory location of GPU? Yes, or internally it is static allocation? No, it's a dynamic memory on the GPU. In fact, on the GPU also inside the kernel, you can use a function called malloc to allocate heap. So there is some heap allocation happening on the GPU side. Okay, so maybe I'll finish this and then we will take a break. So let's say that there is this constant char star message hello world, which is a global variable, the way we were discussing that A should be a global in the previous program. And then I try to print that from the GPU and I call it as dkernel and then CUDA device synchronize. Right. So what happens in this case? Let's think about it. And I'm going to take a break at this stage. We'll meet at 10:50. Right. That is about 7 to 8 minutes from now. Right. Meanwhile, I will take this question. What is the executable file format on GPU like ELF? I'm not sure about that. I believe that it should be something similar, but I'm not sure about that. Okay, so I'm going to stop the recording and we'll sync up at 10:50.